All right, I am going to record this lesson, but again, all you'll see is just the screen. You won't see anybody or hear anyone really but me. Okay. Okay. So before we get into the lesson, a couple of things I want to go over since you guys are starting to get your Chromebooks. All right. So, real quick, Canvas. My Canvas is pretty easy peasy because I put everything on OneNote. All right. Meaning, you click on my Canvas page, this will be the screen that you see. All right. Basically, everything you want from me is within these buttons. I linked everything. All right. So, syllabus, if you want to review the syllabus from that we did yesterday, it's there. Come back to this one in a second. Online calculators. So, I went ahead and linked both the North Carolina Desmos as well as the NumWorks simulator. If you want to use either one of those at any point in time, it's fine. All right, so Desmos, obviously, it's the North Carolina testing version. And then the NumWorks emulator, it's free. You can use it at any time. You can full screen it, do it like that. So if you want to try using the NumWorks before you buy, there you go. All right. You don't have to buy it, but, you want to see what it feels like. Also, NumWorks has a free app. So if you want a calculator like for your phone or anything, it's a free app, and it's exactly this. All right. So that's linked in there just for easy access. And then when we get to it, I do allow test corrections in some capacity, even in honors. But again, it's in some capacity, but when you get to it, the instructions are here. All right. Now, the big one is this button right here, the OneNote class notebook. This is where I link everything, your journal entries, your assignment list, your notes, and the keys. All right. It's just the easiest way to do it for me because it literally updates in real time. So if you click on this link, it'll take you to where you can view my OneNote, which is where what you see on the board. Now, I made a home page. It's basically you treat it like a website. So you can either use these tabs over here or you can use the home page. It'll link everything. So the home page is nice because I went ahead and linked it based off of what unit we're on. So unit assignments, if you click that, it'll take you to the unit 1 transformation assignments. Now, this is where I will actually put in, we haven't had any assignment yet besides the syllabus, but that doesn't really count. I mean, it's going in the grade book, but it's not worth typing in. But I'll put the date assigned, where it is, the assignment link, and the due date. All right, so the assignment link, I will actually link, if it's a paper assignment, I will link it to the paper part, the paper PDF in the OneNote. So like say you lost your packet or something, you can still do it on paper or print it off. All right. Then journal entries. Again, we'll cross that bridge when we get there. I haven't put it in here yet, but all the Unit 1 journal entries will be posted here, so you can click through them. Haven't got to that yet, but by the way, you need your journal or your composition notebook or notebook of some kind by tomorrow. We're going to set them up. Okay? So tomorrow you need to have your journals with you. We're going to set them up. All right, keys, same thing. We don't have any keys yet from homework, but if we have paper assignments, I will post the keys the day after they're due so you can check your work. Especially if it's like a problem that we didn't get to go over in class, because I'm not going to go over all of the homework in class, but I will go over questions that you may have on it. Okay, so this will be the place to check if there's a question we didn't get to or whatever, and you can check work there. I'll have them fully worked out. And then this one's probably the most important, the notes. So this is what you'll typically see when you come into my classroom. All right. How I outline this is I do it by day. All right. So at the top, this was from yesterday. You see the date and you can see everything we did that day. So if you want to know what we did that day, that's where you look. So the mathematic that we did is right here, and it is filled in from the stuff that I did yesterday. The notes that we did do yesterday is still right here. All right, and it's just the part that we filled in yesterday. Okay, Here's today's stuff. We obviously haven't done it yet, but these will be like the notes that we finish up. So it has the ones that we did yesterday because I copied them over, fill out the rest, and today's notes. Okay, this is also where I will post lesson videos. So the video from today I will post under this date. It's by date and by unit. So when we get to unit 2, you'll see another tab for unit 2. And I will change the links in the homepage to open to those current units. Okay, so the homepage is probably the easiest way to navigate, but pretty much anything of importance I'm putting in OneNote because it just makes my life easier. Okay, because I don't really submit anything in Canvas, so Canvas is more of a where you'll get announcements and where you can access the OneNote and any other kind of like online calculators or anything. Okay, it's more of a drop point. Any questions on my Canvas page and how to navigate that or the OneNote? Another thing about the OneNote, if at any point, like let's say that you just can't see the TV for whatever reason, OneNote updates in real time. So as I write the notes, it will actually appear in this in real time. It's like a Google Doc. Okay. So like, let's say that you're having trouble seeing or for whatever reason, you missed a section because I was moving a little too fast. You can always pull it up and check it. Okay. Because again, it updates in real time. All right. So I believe you guys gained access to that today. So at some point when you get your Chromebooks, just check to make sure that you can access it. Make sure you go through ClassLink to get to it. All right. So start the recording. Yeah. All right. So let's finish up the notes from yesterday. All right. So yesterday we started talking about transformations and we were first plugging stuff into functions. All right. So we did the function rule. All right. If we give it a point xy, we plug in to x plus 5 2y to get a new point. All right. We're going to continue that. So let's look at example 2. So example 2, the rule changed. It's now, if we start with the point xy, it becomes y negative x. So what do you think happens? So we're not adding or multiplying anything to x and y. What do you think happens? So if we start with xy, what do you think is going to happen? Just predictions. What's going to change? Okay, it might be a little bit easier if we put the numbers to it. So let's look at letter A. If we start with 5, 3, this is the point xy. How do I change it to look like y negative x? So we're not there yet. I just want to know what we do to the point itself. But good thought. Good thought. Flip what? Flip the numbers. Good. So the first thing is that we're going to flip the numbers to give us yx. So if we flip the numbers, that gives us yx. But that's still not what we want. We want y negative x. So what's the other thing we got to do? Change the sign of the x value. So to make this y negative x, we got to change this sign. So this will be 3 negative 5. And that gives us y negative x. So you guys see how that worked? All right. Let's try letter C. What would it look like? So without doing the 3 steps, what would it look like? Yes. Right, 0, positive 4. So if we flip-flopped it to be yx, it would be 0, -4, and then you have to change the sign of the now y value to be positive. Does that make sense to everyone? How that works? Speak now, forever hold your peace. All right, do I need to do another one? All right. So now that you know how to read these rules, we're now going to use it with an actual figure. Okay, so the function is defined by, if we start with the point xy, we want it to be the point 2x y minus 3. All right, so here are the starting points that they gave us, and they already graphed them for us. Now, does anyone remember what that little tick mark in the corner means? It's not a 1, it's a tick mark. Does anyone remember how you would say it? So a what? What's the word for it? Prime. Good. So remember, this little tick mark means prime, which is just fancy way in transformation land to say that's the image. All right. So this is the pre-image. This will be the image, or what it looks like after we transform it or apply the function to it. So I'm going to list out a prime. Or actually, I'm just going to relist out the original points. So A is -2, 2. B is 1, 6. C is 4, 1. Those are the original points that they gave us. I'm just listing them vertically. Okay. So for A prime, what do I have to do? How do I get the point for A prime? You plug it into the function up here. So what am I going to do? 2 times -2. So I'm going to do 2 times -2. Then what do I do? Not -3 times 2. 2 minus 3. So essentially, I'm plugging in the x and the y in for the x and the y's. I haven't done the operation yet. I'm just writing it out. So my new point would be what? If you do the operations now. -4, which is 2 times -2, and -1. Okay? So for b prime, I'm going to apply the function again. So it would be 2 times 1, 6 minus 3. So what's the new point? 2, not -3, +3. C prime, same thing. 2 times 4, 1 minus 3. What's the new point? 8, -2. And then we're going to graph it and label it. So A prime is -4, -1. And remember, if you do not label your points and it was on your test, it's counted wrong. You have to label your points, meaning you got to put the name of it on there. So that's A prime. B prime is at 2, 3. C prime is 8, -2. So we're not talking about like what transformations happened yet, because it's a pretty funky one. We're not there yet. But this is just an exercise in, can you get new points from a given function in what we call arrow notation. All right, so this right here, this function is given in what we call arrow notation, because arrow. Math people like to name things obvious. We're not the most creative in our naming. All right. Any questions on that? All right, so some definitions on the next page. Transformations. Transformation is a geometric function that takes points in the plane as inputs and gives points in the plane as outputs. So unlike the input just being x in a regular function and then the output being y, we have points as an input and points as an output, so x and y. So the input is known as the preimage, like I said in the previous. Output is known as the image. All right, I already told you that. All right, so take a minute and on your own, I want you to answer A through C. Okay, don't do D yet. I just want you to do A through C. So state out the original, find the new based on the new function, which they gave you here, graph it, and that's it. That's all I want you to do. So take a minute, do that on your own. So don't talk to your group mates yet. I want you to try this on your own first. Thumbs up if you're ready. It looks like it's a good majority. So take a minute before we come back together, confer with your group on your answers. Just compare answers. So talk to all your group mates. Okay, make sure you're talking with your group mates. Oh, sure. I got two. Just like you get 9-6. Oh shoot. 9-6. All right, we're coming back together in 3, 2, 1. Check your answer. So, any questions on this one? So all you were doing was adding 5 to your x values, adding 4 to your y values. So this is about precision. You got to make sure that you get the correct original points to start with, otherwise it messes up your answer. So you got to make sure that you can read those points, and make sure, because sometimes they like to shift the y-axis a lot. So make sure that you look at where the y-axis is. Like, don't just assume it's in the middle. Okay. Now, letter D, I said we do that one together. So is triangle M prime, N prime, P prime congruent to triangle MNP? First off, what does the word congruent mean? It means the same, but what specifically? So same size and same what? Not length. That goes with size. Starts with an S. Shape. So same size, which talks about the sides. Same shape, which talks about the angles. That's what congruent means. Same size and shape. So are they congruent? What do you think? Yes. Because what was really the only thing we did? We just changed its general position. We just shifted it. Yes.
So if every variable is just adding or like subtracting, will it just always be the same? Will it congruent?
Pretty much, yeah. So basically, if you're adding or subtracting to your x and y values, it's going to be a translation, which we'll talk about in 1.2 in more depth. But what this is actually called, this type of transformation, is if it preserves the size and the shape, we call it a rigid motion. So in the land of transformations, all right, we learned about 4 different types of transformations: translations, reflections, rotations, and dilations. Some of them are rigid motions, some of them are not. I'm not going to tell you which ones are which yet, so you probably already know or can take a guess. All right. But rigid motions are just any geometric transformation that preserves the shape and size of the figures, meaning it doesn't change, meaning it makes congruent figures. All right. That's known as a rigid motion. So it means it makes it congruent. Which, by the way, if you need to make a note, this is the mathematical symbol for congruency. It keeps the shapes congruent. All right. Last one. So we're going to do this one quickly together before we switch over to 1.2. So this time, starting with the same points, they already gave it to us, but this time they want us to do 2 different transformations. So F and then G. So they want us to use F to map the original or the pre-image to E prime, F prime, G prime. So function F is what we're going to do to make E prime, F prime, and G prime. So can someone tell me what's happening with the points? They're switching the X and Y, and they're also doing what? They're changing the X value, or the original X value, I should say, to be negative. So new Y, original X, if you want to think about it that way. So if E is 2, 1, what's E prime? If you apply the function 1, negative 2. You flip-flop them, and then you made the new Y value, you flip the sign. I'm going to go ahead and graph it. So that is 1, negative 2. So this will be E prime. Okay, F prime. It'd be 3, negative 8. So you flip-flop them, and then you change the sign of your new Y value. Does that make sense how I'm doing this? Okay, so 3, negative 8. That's F prime. All right, someone different who's not talked yet, tell me G prime. 6, negative 8. Good. So 6, negative 8. Now, they then want us to take the original points again. So we're still using the original points. We're not using the new points that we just found. And we're going to use G, so the formula for G, to make M double prime, because it has 2 tick marks, N double prime and P double prime. Okay, I don't know why they use different letters, but whatever. Usually when you, oh no, I know why. Okay. So usually the reason they didn't name it EFG double prime is because that would imply that we took the prime points and did that transformation to those points, but we're using the original. All right, so tell me what I'm doing, like in terms of what I'm doing to the X and Y values. What am I doing to the X value? Yes. Right, so first I flip the sign of the X value and then divide it by 2. Someone else tell me what I'm doing to the Y. Someone, you're adding just 3 to it. All right. So now, which point is which? You go in the order. So if it says EFG, that means M double prime is E, N double prime is F, and G double prime is P. All right, that's how you read triangle names. Those are the corresponding parts. So M double prime. Okay, so we're starting with E, so that's 2, 1. We're going to make the 2 negative. So what's negative 2 divided by 2? Negative 1. So all I did was just plug in positive 2 into that formula. Okay, that's all I did. And then we just got to add 3 to 1. Three to 1. 4. So M double prime is at negative 1, positive 4. And remember, make sure you're labeling your points, because I'm telling you, if it was on a test, if you did not label your points, I'm taking points off. All right. N double prime goes with point F. So someone raise their hand, walk me through what to do to X who has not talked yet today. So someone walk me through what I'm doing to X.
You take the 8
Uh-huh.
and then you make it negative.
Uh-huh. So we have -8,
Divided by 2.
which is good. Then we just add 3 to the y, so 3 plus 3, that's 6. Does everyone understand where I'm getting these numbers from? Okay, good. So this is -4, +6. So that's n double prime. Then p double prime. That's coming from g, which is 8, 6. So we're doing -8 again divided by 2, which is still -4, and then 6 plus 3, which is 9. So this would be -4, +9. So here's the question. Which of those two transformations, the orange or the pink, is a rigid motion? One of them is, one of them isn't. The orange. So in other words, which function gave it to it? Which function's the rigid motion, F or G? F. Why? Right. So because we divided the X in G, it changed the size. It made it smaller. Didn't necessarily change the shape. If you did the angles would probably be the same. But it did change its size. It made it smaller. So this part right here, the dividing by 2, that's what made it smaller. Okay, so make a note. The first part of your homework tonight, we're not done with notes, but the first part of your homework tonight is pages 3 through 4. All of it. It's only like 8 problems, I think. Yep, it's only 8 problems. Okay. Now, don't start working on it yet. Go to page 5. All right. Now we're going to do some translations. So now we're getting into the specific type of transformation. So the first one was kind of an overview. This one is going to actually be the translations. This one's pretty quick. So, translations is a special type of geometric transformation. Specifically, it's a rigid motion, meaning it preserves the size, preserves the shape, makes congruent figures. So, another name for rigid motion is called isometry. So if you ever hear the word isometry, that's just another name for rigid motion. Okay, they're synonyms. So rigid motions and transformations are transformations that have these specific characteristics. They map lines to lines, rays to rays, segments to segments, which is just a fancy way of saying like if you are given a line and you translate it, it's still going to be a line, not a line segment. If you translate a ray, still be a ray. If you translate a segment, still be a segment. All right. They preserve the distances between two map points. So, in other words, they keep the same size. And they preserve the angle measures between two map rays or lines or segments, which is just fancy for saying same shape. So size typically deals with side lengths, shape usually deals with angle measures. Now, the rigid motion knows a translation. Before we actually talk about, we got to consider the concept of a vector. So, vectors you see a lot in physics, okay, or more advanced calculus, but we do see them a little bit in geometric transformations, at least the easier versions of them. You're not doing anything funky with it, like I had to do in calculus when I was in college. But vectors is technically a physics thing. All right. So a geometric vector, or just a vector, is a straight line distance in a particular direction. It can be a line defined by a line segment designated by a starting and ending point. So it tells you where to start, it tells you where to stop, and it gives you direction. So a vector is basically distance and direction. Okay? That's how you can describe a vector: distance or length and direction. So we're just going to start by drawing vectors. They want us to draw a vector from A to B. So where do we start? A. So A is where we start, and you're just going to draw a straight line to B. Now, so we know the direction, we put an arrow of where we start. So what we just drew right there is a vector. Okay, so remember, it's distance and direction. So if we measured this length, I don't know what it is, but if we measured it, that would give us the distance. The arrow tells us the direction. Now we're going to do E to D. So start at E, go to D, make sure you draw the arrow. And then Q to R. Start at Q, go to R, make sure you draw the arrow. Those are all vectors. And they look like what? What type of geometric figure do they look like? Rays. All right, so a lot of times with geometric vectors, you'll see them as rays. Now, how do you think vectors connect to translations? What is actually a translation? Yes. It's just moving points, or what's a better word for moving? Shifting. It's just shifting points. Are we changing anything size-wise? No. So how do you think vectors connect to translations? Think about the definition of a vector and the definition of translation. How does it connect? Say it one more time. One more time. I got the fans in my ear. Sorry. You can find it using a given vector. Yes. But I want why we can find it using a given vector. I know you two know. I want something different because you guys have talked a lot. Kind of.
When you shift the points, they're going certain directions and going certain distance.
Right. So that's how the vector connects to the translation. Translation is you're shifting the points in a specific direction for a specific distance. So like when they say shift right 5, right is the direction, 5 is the distance. So you're literally making it a vector. All right. So basically, that's just a restatement of that. Translation maps or moves each point of plane a certain distance in a certain direction. And this can be defined by a given vector. So it may be a little light on your side, but they gave us points and they also gave us the vector. to give us A prime here. So they already went ahead and plotted A prime. So here's the question. How did they get from A to A prime? What did they actually do graphically? So in terms of direction and distance, what did they do graphically? Over what direction? Right. So it goes right 6. Yep. So right 6. And then I heard the other one. What was it? Down 3. So make sure you include the word shift. Right 6, down 3. Now, what's another way you could kind of describe what you did to find that? What's that like similar to? So we went, I heard it. What was it? Slope. We shifted right 6, down 3. You could think of it as like rise over run. Find the slope of the vector. All right. Just, you don't have to make a negative because they don't care about that. Well, I guess if you want to, it could. Oh, I guess it is. Yeah, the negative emphasizes the down part. So, how would I actually write that as a function like the ones we did back in 1.1? Yes. Okay. How'd you get that? Or how'd you figure that out? Good. Another way you could have figured it out is if you looked at the x values, you ask yourself, how do I go from -3 to 3? What do I have to add or subtract? So that's adding the 6. How do I go from 6 to 3? That's the subtracting the 3. All right, so if we follow that rule, what's B prime? Someone who has not spoken yet today. What's B prime? I don't know your names yet, so I can't start doing popsicle sticks. So what's B prime? We know the rules, so that should make it a little bit easier to figure out what the point is. You don't really have to use the graph. So B is 3, 8. What's B prime? Yes. 9, 5. Good. 3 plus 6 is 9. 8 minus 3 is 5. So B prime is 9 up 5. So right here. Someone else, what's C prime? Yes. 2, -1. -4 plus 6 is 2. 2 minus 3 is -1. Good. So 2, -1. Did that make a congruent figure to our original? So again, it's kind of hard to see because I drew a lot over it, but the original's right here. Is that a congruent figure? Is purple and green the same? Yep, just moved his position on the board. Still the same orientation, it just kind of slid. It's kind of like chutes and ladders. It just went wee down the slide. All right, any questions? Okay, so we can express translation using arrow notation like we've been doing, or like we've kind of been using to find different points in the previous lesson. So what do you think a general rule would be? So what do you think is the general rule? If you start with a point x, y, how do you figure out if it's a translation? Or how do you know if it's a translation or not? Look back at the previous problem. What did we do to represent translations? What operations did we do? Addition and subtraction. So how do I write that? So we know we have x, y, and we have some number. Let's say that those numbers are a and b. What sign would I put between them? Not quite, but you're on the right track. I want to combine the fact that I can either add or subtract. The plus minus sign, good. So this is the general rule. We don't know if we're adding or subtracting, but we know we can do either or. All right, depending on what the actual transformation is. So the plus minus just says that we can either add it or subtract. And again, A and B are some random numbers. Not necessarily the same numbers, they're just numbers. Okay. Now, for x values, what direction is plus? That's right. Good. Pun not intended. What's minus? What direction? Not down for x. Left. So the way you can remember which one's which, x-axis is horizontal. So horizontal, you can only go either left or right. So the y's, the plus would be what? Up. Minus would be down. Way you can remember that, y-axis is vertical. The only directions you can go is up, down. Treat it like a number line. All right. So another way to write this rule is, and this is, you may see it like this, is a capital T and then there's two ways they may write it. You may see it with like this type of bracket, A, B. That's actually the vector. Or you'll see it as capital T with AB with no brackets around it. Where A and B still represent A is what's done to the X, B is what's done to the Y. All right. This notation is called function notation. So the two types of notation that we look at is both arrow and function. You can see it in either way. You got to be able to recognize both. And again, function notation, it just depends on who, for at least translations, it just depends on who wrote it. So sometimes you'll see it with the vector symbol, which is what kind of the greater than, less than brackets on either side look like. This is actually representing a vector. Sometimes you see it without brackets at all. All right. Okay, so example 3, we're going to draw J. So 0, 2, 3, 4, and 5, 1. Right, there's our triangle. They then want us to find JKL prime by doing a translation of 4 units left, 5 units up. So we're going to count each point. We're going to go to the left 4, so 1, 2, 3, 4, and then up 5. 1, 2, 3, 4, 5. So that'll be J prime. So if I were to draw a vector between the two, that would be what the vector looks like. You're going to do the same for all three. So over 4, up 1, 2, 3, 4, 5. There's K prime. L over 4, up 1, 2, 3, 4, 5. L prime. And if you want to look at it in terms of a vector, you can actually draw the vectors. Oops. And aren't those vectors the same slope? Yes. Jordan, Miss Smith wants to see you in the counseling office. Okay, so what are those new points? What's the new point for J prime? -4, +7. Good. Wait. Yeah, I was looking at the wrong thing. Okay, someone else. K prime. What's the new point? You in the back. -1, 9. Good. Last one. Someone else. 1, 6. Good. So, based off of the points, what would be a good rule to write using arrow notation? So, if I start with XY, what does it become? So, think about how you get from J to J prime, K to K prime, so on and so forth. So, for the X value, how do I get from 0 to -4? You subtract 4. To get from 0 to -4, you're subtracting 4. So it'd be x minus 4. Does that work as well for 3 to -1 and 5 to 1? Right. 3 minus 4 is -1. 5 minus 4 is 1. So it works. You got to make sure it works for all your points. That's a good way to check yourself. All right. Y's. How do I get from 2 to 7? +5. Does that work for 4 to 9, 1 to 6? Yep. 4 plus 5 is 9. 1 plus 5 is 6. Does that also line up with what our original rule was in words? Yes. Left 4, that's -4 to the x's. Up 5, that's +5 to the y's. Now, are the two figures similar or congruent? So we know what congruent means. Can anyone tell me what similar means?
But like it's the same shape, just different size.
Right. So, similar just means same shape. Congruent is same shape and size. Okay? So are those two figures congruent or similar? They're congruent. Why? Right, because we only shifted the points in a certain direction. So in other words, we didn't change or dilate the points at all. We didn't kind of multiply or divide anything to it. All we did was move it in a specific direction. Does that make it easier for y'all to see? That's another thing. If I have to zoom in or anything, let me know. You're not going to offend me. All right. So These next two, we're going to kind of skip the whole graphing bit because I can trust that you guys know how to graph, right? I just want to determine the points, okay? So we're starting out with the points T, U, and V. And you guys are okay with me not graphing or anything, right? If you want to graph those yourself, you're welcome to, but I'm just not going to for time's sake because we're almost out of time. So, first off, how would you describe this rule in words? What are they doing? Good. They're going to shift. Don't forget to include the word shift. That's the key word that says translation, translation, translation. Shift left 3 and then down 1. Any questions on that? So, we don't have to do C because that's using the graph. What's the new point for T prime?
-3, 2.
-3, 2. You subtract 3 to 0, subtract 1 to 3. Someone else, U prime. -1, 3. Good. And V prime? Yes. 2, -2. Good. Now, we're then going to use the new image that we just came up with, so the TUV prime, to perform this translation. So before we even get the coordinates, what's the words? We're going to shift. So right 3, down 3. So what's T double prime? Remember, you're doing it to the T prime. You're starting at T prime, going to T double prime. 0, 5. Add 3, 0, minus. No, it's not +3. It's -3, so it'd be -1 actually. What's U prime? 2, 0. Good. V prime or V double prime, sorry. +5, -5. Good. Now, here's my question. Based off of just what we did algebraically, not really algebraically, but numerically, do you think the double prime image will be the congruent to the original? Like not to the prime, but to the original image, what we started with? Yes. Because again, all we did was just a translation. Translation is a rigid motion. Now, the fact that we did 2 different transformations to get from TUV to TUV double prime, all right, that's known as a composition of transformations, which just means more than one. But what could I simplify that to? Because all we did was 2 translations. So technically, we could just make it one big translation. So look at the points for TUV and look at the points for the double primes. What could be a straight shot translation? So let's write an arrow notation first. If we start with XY, how do I get from 0 to 0? Nothing. So what do you think I'm going to put for X's? No, you still have to put an X. You don't even have to do that. Because if you add 0 to X, what is it? Just X. So you just leave it as X. I know it's small. Okay. How do I get from 3 to -1? You do what? -4. So that's our rule. That works for 2 to 2, 4 to 0, 5 to 5, -1 to -5. So in words, what would that translation be? Just shift down 4. So we did a whole hullabaloo of transformations just in reality to shift down 4. All right. Okay. So the other part of your notes is going to be pages 7 and 8. Also relatively short. Yes. Yeah. So your homework for tonight, and I'll put this in OneNote, is pages 3 and 4, 7 and 8. I will check it tomorrow. All right, you got about literally a minute, so you guys can go and pack up. Make sure your name tags are back in the bucket before you leave. So make sure your name tags are back in the turn-in box before you leave.